So in previous lecture, we were talking about introduction to the cash and the basic caching, and the example today we are going to talk about the cash placement policies, cash replacement policies, and the right strategy, which are most important to talk about that. So we'll quickly get into the cash placement policy. As we know that when we fetch a cache line, when we fetch a cache line from the main memory, how we are going to place it in the cache. Okay. So then let's quickly get into that in cache placement policies, that for a cache line, which frame slot in your cache, which frame slot, we know that the cache is made up of your frames. Which frame slot should be stored the cache line? So to do that, there are three types of cache placement policies are there. One is direct mapped caches, fully associated caches, and set associated caches. So we'll go in one by one with their algorithms, mapping algorithm, and their with an example. So see, in the before getting to this cache, the direct mapped caching or your fully associated caches or set associated caches, one needs to understand what is the cache line address. What is the cache line address is there. So consider a cache line, suppose in our memory, as we said, the memory, in the main memory, the memory is partitioned or organized as rows and columns, and every block is treated as your block or cache line, or simply we can call as your line. Okay, so if the cache line size by definition, we say that a new cache line always and whatever the size is there, if the size of cache line is suppose 64 bytes, so this size is always writes in terms of 2 to the power of s. Okay, that means in the 64 bytes, we can write this as your 64 bytes of size of your cache can be written as 2 to the power of 6. So here we can say that s is equal to 6. One should remember this one. If suppose the cache line size is suppose 32 bytes, then it can be written as 2 to the power of 5. In that case, your s is equal to 5. So consider a cache line with any size that should be written in terms of your 2 to the power of s bytes. So the last s bits of its address, the address of this cache line will be always be 0. That means in that memory, let me just write for one cache line, one column of this one. Okay, in that whatever cache line is there, if that cache line size, suppose if you take it is a 64 bytes. So the starting of this cache line starts with 0 and ends with your 63. Then the next cache line starts with 64 bytes and ends with your 127. And the next cache line starts with your 128 and ends with your 191 cache line. So if any cache line, the starting bit, if you're going to write this address, any cache line address, okay, so by definition, a cache line always starts at the address which is multiples of your 2 to the power of s. For example, if a cache line of size 64 in this case, then it is 2 to the power of 6. So in that case, if you take any of the cache line, in this case. So let me just write for 0, the starting address, starting byte of this cache line, first cache line is suppose 0. If you write it in binary form, that the in the binary form, if you write by using suppose 4 bits, 8 bits, suppose 000 and 000, right? So this is 64 bytes, means it takes the 2 to the power of s means 6 bits. So all the last 6 bits are always 0. So if you take the 64, the next cache line, if you write this its binary form, its binary form, it gives is 0100 0100 So last six bits are zeros in this case, right? If you take the next one, suppose next line, it is 128. If you write it in the binary form, you will get 1000, then 0000. So all last six bytes, all last last six bits are zeros. So it shows that by a cache line may start at the address either 0, 64, 128, or etc. The binary representation of these addresses are this. So the last six bits are always 0. So note that the last six bits are always 0, means it is starting a next cache line. Okay. So from here, if you see, let me just clear this. So this is how the cache line started, and it's addressing the cache line addressing. But there may be a chance that in that cache line, suppose let us take the first cache line. In the first cache line, for example, in the first cache line, it starts with 0. Right? Ending with your 63. Okay, but in between, always if the cache line starts, means the last six bits are zeros, but there may be the arbitrary piece of data in that cache line. Suppose the data is at the address, suppose the 30, or at suppose 69, at suppose 30, and the data somewhere in the 60th byte. This is the first byte, second byte, third byte, and goes on. 60th byte. Then how would you write? If you write that 30, if you write in the binary form 0b, the binary form, you will get the 001, 0001, and 1111. If for this arbitrary piece of data that is at 60th byte, suppose the 60th byte, suppose, then the binary form of that, you will write 0011, 0011, and 1100. Okay, this is one case. Suppose if you take the second cache line, your second cache line starts at 64 and ending at the 127. And consider that somewhere in between, the arbitrary data in between, suppose at 70 and at suppose 101, 111, suppose, arbitrary data address in binary form that you can write for 70, it is 0100, 0100, and 10000. And for the arbitrary data address of your 111, you may write in the binary form that the binary equivalent form is 010110, or 1111. And similarly, if you take the third cache line, suppose if you take the third cache line starts at the 128, and ends at the 191, because the size of these caches are your 64 bytes. 64 bytes. So assume that the arbitrary data at location in this cache line is at suppose 129, and another one is suppose at the 169. So if you take this binary address 120, 129, this is gives you that 1000 in the binary form, 1000 and 0001. For 169, you can write the binary form at your 1010, 1010, and 011011. Okay. Now see this, the beginning of addresses having the last S bits. The last S bits are 0, but for any arbitrary value, inside this cache, the last 6 bits are not zeros. The last 6 bits are not zeros. If you take here, the last 6 bits are not 0 in cache 1, in cache 0. Here also the last 6 bits are not 0 in cache 1. In the last 6 bits are not 0 in cache 1. But if you clearly observe that, for any arbitrary data, in that cache, the first 2 bits are common. The first 2 bits are common. The first 2 bits are same in all these cache lines. Okay, for these addresses, the first 2 bits are same. So what I mean to say here is these last 2 bits indicates the index of your cache. We call them as cache line index. Cache line index. So in the cache line index, for this these arbitrary data addresses, the index is 0. Okay, for this the last 2 bits is index is 1. For this the last 2 bits gives the index is 2, and so for any of the address. So from this, for beginning of the address, last bits are 0, but the first 2 bits indicates the index of your cache line. Index of the cache lines. Okay, so from this we can conclude that as just discussed, for memory addresses the last bits are 0. So from this we can conclude that the address of any arbitrary data, arbitrary piece of data, that is separated into, for some offset, the last few bits are non-zeros. So we call the last bits, we call this as your offset in that. So these last 6 bits indicates the 30, 60 and those, and first 2 bits indicating the index part. Okay, so the address of your the cache line address is categorized into and separated into 2 parts. One is your offset part, another one is your cache index part. Okay, for offset it is using the last S bits for your offsets, and remaining bits of your address used for your cache index. So as said here, for an arbitrary piece of data, the last S bits of its address does not have to be 0. So if the last S bits of the memory address piece of data are not 0, then this data must be inside a cache line, like it may be at 30, at 70, as said, inside a cache line, it may be at 30, at 60, or at 70, or 101, a different location, right? So the last S bits gives the location of the data within its cache line, and we call the last S bits as your offset. And for a piece of data address, suppose this one, that is the hexa value of this one, it is equal to 129. That is equivalent to this one which we observe. So the offset will be the last 6 bits. The offset will be the last 6 bits in the 129, that is your last 6 bits 000001 are the offset value, and first 2 bits are your index values. First bits are your index values. So that is in the cache line address. This is very important. In cache line addressing, it is in two parts. Last part is offset. That offset gives the exact location of the data in that cache line, and first part, that is the index of the cache line, in which index that data is available, right? So an illustration of the memory address with the offset and cache line index as just drawn in the previous slide. Okay, the last bits are your S bits and first are your cache line indexes. So for an address which we have seen for the 129, which is equivalent to your 129, so the last 6 bits are your offset and first 2 bits are your index 10. That is what we have seen here for 129. Okay, right. So then comes to the direct cache memory. By understanding that cache line address, now we'll jump into the cache placement policies. In that, the first one is your direct mapped caches. In the direct mapped caches, what it is there that first it is going to map the main memory with your cache memory. In direct mapped cache, it is going to map the main memory with your cache memory. So this is your cache, and this one is your main memory. This one is your main memory. Okay, so in the main memory, you will have the cache lines. You will have the cache lines or blocks. Similarly, in your cache, you are having the frames. The cache, you are having the frames. So how many frames it is going to generate means, for 2 to the power of, you can say that 2 to the power of n frames. 2 to the power of n frames will be there. Okay, and in the cache memory, as we said, now the cache line is using the cache index, that is your 0, 1, 2, 3, and so and so. So in direct cache memory, okay, we have already seen this example in the introduction to caching, but the placement policy of this cache in direct cache memory, it says that the 0 index, here the frame index is also there, the frame index will be there. Okay, so 0 indexed cache line will go and take place in 0 index frame 1, 2, 3, and this goes on up to 2 to the power of n minus 2 to the power of n minus 1 frames. Okay, similarly, 0 cache line goes and store into your 0 frame, 1 cache line go and store into 1 frame, 2 cache line go and store into 2 frame, 3 cache line go and store into 2 frame, like that 2 to the power of n minus 1 cache line go and store into 2 to the power of n minus 1 frame, and if it is having 2 to the power of n 2 to the power of n the next one, 2 to the power of n for cache line, it goes and store into the first frame of your n frame, 2 to the power of n frame cache. Similarly, 2 to the power of n plus 1 cache line, 2 to the power of n plus 1 cache line will go and store into your the frame index 1. It is going to store in 1, and so on. So it calculates. So how the mapping algorithm says, the mapping algorithm basically calculates that the frame index for given the cache lines, the cache line index, given cache line index, that is the indirect mapper, that the cycle, the cache line index, do the modular operation of 2 to the power of n frames. In this case, 2 to the power of n frame. So this modular, the operation will take to directly map the cache lines into this one. As we have observed in the previous, during our introduction to cache, that there will be only one in this direct mapped one. There will be only there is only one slot, or only one frame index is reserved or dedicated for any of these cache line, dedicated for any of these cache lines. So as said that, how to calculate the size of this cache means, if there are 2 to the power of n frames are there, and every can come and take place in this, then the cache line size is, we write it as 2 to the power of s. As we know that if it is 64 bytes, then it can be written as 2 to the power of s. So means here s is equal to 6. But if it is x bytes, then it can be written as 2 to the power of s. So the size of this cache is multiplied with 2 to the power of s multiplied with your 2 to the power of n. So that is your size of cache. Your size of cache is equal to 2 to the power of s, the size of your cache line, multiplied by the number of frames in the cache, that is 2 to the power of n. That gives the size of your cache. Right? So yeah, this is the one which we just explained, that the simple example we have seen, that the placement policy for 2 to the power of n frame slots with a cache line of 2 to the power of s in size, then a piece of data at the address, suppose A, at this address, suppose A address. So let its cache line index be this CXI, as said here, the cache line index, then that will be given as the frame index will be calculated as your cache line index modular of 2 to the power of n frames. 2 to the power of n frames. So this is the example given for that, for this the discussion. So then comes to in what is most important one in this direct mapped cache one, means calculating this frame index. Calculating this frame index based on your cache line index, doing the modular operation of 2 to the power of n. So here the modular operation will be taken. So to make this modular operation faster, let me just recall you how to do this modular operation. So to determine the f index to store the cache line, we are performing the modular operation. In this modular operation, for example, let us consider the example of your decimal modulation, modular operation. Your decimal. In decimal modulation, suppose if you have the number that 789 modulo of 10, then it will take the last digit as a result, that is 9, right? If it is suppose 789 modulo of your 100, so this 100 can be written as 10 to the power of 2. So last two digits will be taken as a result of this modulo operation 89, right? Similarly, if it is 789 modulo of suppose 1000, then it can be written as 10 to the power of 3. So three digits will be taken as a result 789. So from this scenario, if you see that if you have any number, suppose x, that the x number of modulo of suppose 10 to the power of n, then it will take the last n digits, or last n digits. The result will come to the last n digits of your number x, right? In the same way, for binary also, we do the same operation, the modular operation, to make simplicity for mapping the cache line index into your frame index. That was, suppose for any binary number y, modulo of your 2 to the power of n, it takes the last n digits, or last n bits last n bits of the binary number y, of the binary number y. For example, suppose if I have the binary number, uh, for example, the binary number of suppose 101101 modulo of suppose 2 to the power of 4. That means it takes the last 4 bytes as a result, 4 bits as a result, that is 1101. Suppose if I take that the binary number of 101101 modulo of suppose 2 to the power of 5, that means the last 5 bits will be taken, that is your 01101. So from this, what I mean to say that when you are doing the modular operation, why you're doing this modular operation to perform, doing this modular operation to perform the to find the frame index, to find the frame index. That frame index comes from your cache line index, and there you are performing from the cache line in the, on this cache line index you are performing with modular of your n bits. So these n bits, so how the last n bits are taken, the last n bits are taken. So this to the power of n means the last n bits will be taken from this number, that will give the address of your index of your frame, that will give the index of your frame, right? So from here, if you see, let me just recall that we have seen that for any arbitrary data in the cache line, in the address of any arbitrary data, in the cache line, that we have seen that that is categorized into two parts, right? One is your S bits. S bits are we call the offset. Okay. So this offset gives the what is the exact location in this cache line. For that, you are using the S bits. Okay. Right. Now, to make this frame from this cache line, from this entire cache line, suppose let us say here, from this cache line, few bits are identified to locate the exact data. Okay, and then this cache line, entire cache line is going to store in this frame, right? It is going to store in this frame. For that, whatever the remaining cache index is there, we call the we describe that this field is your cache index, right? Cache index is used, as we have seen in this discussion, in the cache index. Then from that cache index, it takes as to the power of n, or to the power of 5 means it is taking last 5 bits. So last n bits here, to the power of n frames means the last n bits are used, or last n bits are taken to find the direct frame index, and remaining bits will be treated as your tag address, or the address of your cache line. So this is the major important part to understand in direct mapped caches. Okay, last 6 bits are used for your offset purpose to locate the data, and the lower n bits of your cache index is used to to map the this cache line into your frame index, and the remaining bits are used for your tag purpose. So if you recall in our previous lecture, for every frame is having 3 fields, right? Every frame is having 3 fields. Okay, every frame is having 3 fields. First field is your tag field, second field is your status bit, third field is your data bit. So this tag address is going to store in this tag of your frame once the frame index is selected. So in the frame index, in our previous discussion, we called this frame index is nothing but your slot. Okay, so that slot will be selected first based on these n bits. The slot will be selected. Okay, after slot is selected, then the the tag will go and take place in the tag field, right? So from this, as said, the first modulo operation, as just said, the last S bits are your offset, the lower n bits for your indexing, the frame index purpose, and the remaining bits are used for your the cache line index. So from here, how this directly map will take place means, let me just recall that the cache is having the number of frames, In that frame, every frame is divided into, it is having three different components. One is your tag, another one is your status bit, another one is your data bit. Along with that, you are having the frame index, we call that as your slots, suppose. Okay, slot, that 0th slot or 1 slot, 2 slot, or we call this as your frame index also, right? This how it works. Okay, this is your cache, how it works in direct map caching. In direct mapped caching, whatever the memory address which is requested by CPU, that memory address, as we just saw here, this cache line address, or this address, in this address, the first it takes the index bits. So those index bits are given as an input to a hardware component, that is decoder. So this decoder is connected to every slot. This decoder is connected to the decoder is connected to every frame or every slot of your cache. Okay, so then once this index is there, once it is given as an input to a decoder will select the valid tag. Decoder will select the valid tag based on this input. The decoder will select the valid tag, the valid the index file means valid slot is selected. Valid slot will be selected. Once valid slot is selected, in that slot you will have these three fields, right? In that slot you will having the state field, tag field, and data field. Okay, so once that frame is selected, this frame is selected, then from that it will take the tag, and give as an input. It will take the tag, give as an input to the comparative hardware component. So then from here, the tag will be selected, tag will be given as an input to this comparator. If both are matching, then there is a hit. If not matching, then there is a miss. In our case, let us assume that both are matching. So then there is a hit. When there is a hit, then the data field of data component of that frame is taken. And this data component is very big, but your CPU requires only a piece of data from that the entire cache block. So from there, the offset will be taken from that offset. This offset will be given for the selection from this entire block. Based on this offset, which piece of this block is there, that will be selected, and that word will be given as an input to your CPU to perform the computations. So the index bits are sent to the decoder, and which activates the corresponding frames. Are your slot, and then for a tag comparison. After that, doing the tab comparison, if it is matching or not. If it is matched, then the word will be fetched out. So this is the concept of your direct mapped caching. Let us see that with an example. So in this example, if you say we have a cache with 4 frames, 4 slots are there. Okay, that is 2 to the power of, the cache line size is 64 bytes, and the given references are your 00. So here the address size which we are taking, is your 12 bits address. Okay, in that case, in this cache frame, in the cache, in the frame, when you talk about this cache line, then the last 6, this is 64 bits means 2 to the power of 6. So S bits are your 6 bits, then it is having only four slots, so that you can write 2 to the power of 2, so that is giving four locations. So this 2 is your number of bits will be taken for indexing, that is 2 to the power of n, uh, which we have said here, the 2 to the power of n bits here, 2 to the power of 4, 2 to the power of 5 means that gives 2 to the power of n. So from this slot, we will get n is equal to 2. So 2 bits for your the frame indexing, and remaining bits out of 12, the remaining 4 bits will be used for your tag purpose. Okay, so let us see for these given reference to the memories, like I have written for simplicity purpose in hexadecimal. Okay, so let us take the first data, the first memory which is requested by CPU, then how it will be doing the direct mapping in the cache. So initially cache is empty, so the valid status bits in this cache is all are zeros, and the slots there are 0, 1, 2, 3, 4 slots are there. Okay, so for the first attempt, the first data which is accessed at the location 0, 0, so the binary equivalent of this one is written in 12 bits, that for every 0 there are 4 bits will be taken. So from this, as we know that the last 6 bits are your S bits, and then these 2 bits are your N bits, the remaining are your tag bits, okay. So the cache line beginning address is your 000. So taking the equivalent value of that one, it gives the index like 00, so slot will get the 0 index, and the tag that we can write as your in hexadecimal form as your 00, right? So from this, the index is 0, so 00 is selected. In that 00, in our previous case, the slot 0 does not have the valid data because it is having 0 only, right? So then in the zeroth slot, your data, the cache line is fetched from the main memory and stored into data field, and set the valid data, the validity of this data as 1, and store the tag address as the tag address from cache line, that is 00. So in the hexadecimal form, I'm using this for the simple writing purpose. So 00x, so that will be stored. So when it goes to the second case, okay, when it is accessing second data accessed at location 0110, so its equivalent binary form is this one. So the offset is your 00100, and the cache line beginning address is your 0 in hexadecimal form, that is 0. The 100 if it is calculated, then the index from here is, it is taking these 6 bits for your S, and this one is your index. These are your beginning of your address. So index is 0, and the slot, the slot is index is 0. That means the slot ID is your 0, and the tag address is your 01 from here. So slot 0 has the tag 00, So it does not match the tag 01. It does not. This tag is not matched with the does not match with the tag 0. 1. So thus a cache miss to the slot 0 is there. When cache miss to the slot 0 is there, then data from this 000 hexa value will be received and replace the data from your 0100. So that will replace it. So when the third the data accessed at located at 00, then the binary form of this one is this. The offset is this one. So your offset is this one is index, and this one is your tag value. So then first it goes and check in the 00 index 1, the 00 index 1 is there, so the data is valid. Then it is going to compare this stored index, compare with the stored index. Previously it is 01, right? For third, when it comes to third one, this 01 compared with the upcoming one, that is 00, that is not matching. So when that is not matching the entire frame, this entire frame is deleted, and the new data will be stored, that is at location your 000. Okay, that will be stored, bit set to be validated, and the tag is set to a new address at 001. And this again, a cache eviction happens here. Okay, then goes to your next address, which is given 0108. In there also the index is 0, that slot is 0. In slot 0, valid bit is 1, but the tag is not matching. So again here the enter frame will be deleted, and the new cache line will be stored here, that is from the address 100, Okay, so here the third eviction while the cache has empty slots. So from here you can see for the next address, that 0058 05C, there again it finds the slot is 1, so new slot is selected. In that, the previously it was 0, so then the data will be fetched from main memory and stored into the data, which is at the location of X040. Okay, and here the slot 1 does not have a valid data, thus a cache miss to slot 1. So in this the next one, again the address slot ID 2 is selected and the tag address is 01. So slot 2 does not have the valid data, thus a cache miss to this 2 again. So that will be fetched from the main memory and stored into this data. Right. Similarly, for the next address, that is a 088. So for that, the slot 3 is selected from this binary form, because it is these two indicates the 011. So that the third slot will be selected, and third slot does not have any valid data. So thus again the cache miss happened here. Okay. So then it will fetch the data from the main memory and store into your data field of your cache. So what are the pros and cons here? Means it is very easy and fast to compute the frames or slots index given an address, but fast index calculation that allows quickly determine if there is a hit or miss. But easy computation also simplify the hardware implementation. But the problem are the con here is, then can this direct mapped caching can have the high cache miss rates. Even if there are still many empty slots, then in the cache, if you take in these cases, there are many empty slots, but still they are going to occupy the same frames. So that's the reason many miss rates are there. So in our previous example, there are 100% miss rates are there. So certain memory access patterns may always experience these cache misses. So to overcome from this problem, there is the advancement of your direct memory cache is your fully associative cache. In this fully associative caches, a cache line can be mapped into any of the slot. In our previous case, if in direct mapped class, zero cache is there, means that is going to store in 0 frame only. If one cache line is there, means after doing modular operation, if it is allotted to slot 1, means it is going to take place in 1 only. Okay, if it is 2, means it's going to take place in 2 only. 3 means take place in 3 only in the cache. But whereas in fully associated, it says that if the first frame goes and take place in this cache, suppose the frame 1, the cache line 1 taken here, then if the second cache line is also required the same, but there are empty slots are there, means any of these empty frames will be given. That is first in, first out, the empty filling will be given. So when a cache miss happens for a data at address A, then if there is an empty slot in the cache, use the first empty slot to store the cache line of the cache line index. So if there is no empty slot, then cache replacement policy will be taken place, that we will discuss. Okay, yeah, but in our discussion we'll take that the first in, first out cache replacement policy. Okay, is used to select a non-empty cache line to store the cache line of the cache line index. So the old data at the selected non-empty slot will be evicted, and this evicted cache line is called the victim part. and typically the cache replacement policy will select the oldest or the least used cache slots to store these the upcoming cache lines. So more on cache replacement policies we'll discuss about this one. Least recently used or most recently used, that we'll discuss. So in this case, as we are saying that since a piece of data can be stored in any of the frame, that means frame index is not required from the address of your cache line. So only the offset is required, and the remaining bits will be used as your tag. So suppose for this address, suppose for 129, so the binary form of this one, the last 6 bits, this 1, 2, 3, 4, 5, the last 6 bits, they are used for your S-bit purpose, offset, and the remaining bits will be used for your tag purpose only. So there is no, in fully associative, there is no what you call the frame index concept. Why? Because any empty frame can be selected to store the newly upcoming cache lines. So in that, in the hardware implementation, how we do, first when the request comes from this address, when the request comes from this address, when the request comes, okay, then first in the cache line, as we said, it is having the 3 field data field, the status bit and your data bit and your tag. Okay, so like for every frame there will be a tag, so that tag will store this tag will be the tag of your cache line. Okay, so upon having any tag, the request from this, if any tag comes, that tag will it fetch all the tags from your cache, and from all the tags the comparison will be done. So compare the tag, the requested tag with the first tag, second tag, third tag, fourth tag, until the tag matches. Once the tag matched, then after doing this comparison, once the tag match means there is a hit. When there is a hit, then from those slots, in this hit, from those slot, all these data frame will be taken from all these tags. One side the comparison will be done, in another side all the data will be taken from this frame, and that will be given as an input to your multiplexer. Upon this tag is matching, from that tag, suppose this tag is matched, okay, from that tag the data will be taken. So whatever input is given to multiplexer, this data will be given as an output. Once the data is selected from that tag, then use the offset. That offset is used to select from that data which part of your word is requested by your CPU. That word will be selected and given to your CPU for your computation. So this is fully associative. So with this, what happens? The number of misreads will be reduced. So let us see this with an example now. So consider again, there are 4 frames. The 4 frames are there in the cache. So there are 4 slots, and every frame is having 3 fields: tag, valid data, validity, and your data field. So there are 4 frames are there, means it is it is going to write that to the power of 2. So here you are having this 2 to the power of 2 means 4 locations in our cache. Okay, so just remember that from our address line, we are for fully associate, we are just taking only S bits, and the remaining bits are your cache index only, and that will be used for your tag purpose. So the cache line size is 64 bytes. 64 bytes means 2 to the power of 6 is equal to 64 bytes. So 6 is your S is equal to 6 bytes. So it takes, these are 6 bits. Remaining 6 bits are used for your tag purpose. So the reference address which is given to us here is the same reference address which we used for our direct map 1. Okay, and let us see. Initially, this cache is empty, so all these bits, the validity become your zeros. All these bits become zeros. When this becomes zeros, then from this address, if you take this, the binary form of this, initially it is zero. So for the accessing for the data access located at the first zero zero zeros, from there, the binary form of this one is a. So you can see the first 6 bits. The first 6 bits are your S bits, and the remaining 6 bits are your tag bits. Your tag bits. Okay. So right. So then what it happens? It is going to first search in the tag. Search this tag bit will be given for the comparison. So initially there is no tags are there. So when comes, that will, for comparison, nothing is there. So then the cache is empty, so cache miss occurs. So pick the first empty slot. The first empty slot, it follows the first come first serve. First come first serve. It follows the first slot, and so that is slot 0, to store the cache line of your address, this one, the tag address, your 0000. So its a hexa value is, you can write as your 00. Okay. So next, you can see the next address is the next second data access, which is located at the 108. Located at 108. Its binary equivalent value is this one. So last 6 bits, they are S bits. Okay. And the first 6 bits, they are your tag bits. They are your tag bits. So this first 6 bits, if you write equivalent into, that is your hexadecimal of your 0, 4. So now this 04 is compared with the previous one. 04 is compared with the previous tag. If it is not matching, then there is a data miss. There is a data miss. So no slot has 04 in the cache, previous cache. So the cache miss occurs. Then pick the first empty slot. Pick the first empty slot means this one is already busy. So pick this slot, and bring that cache line into this data field of your frame. Then set the validity bit as 1 and set the tag address as your 04. Then go for the third case. In the third data access, again it is taking that 00. So that equivalent value is this one. So its hexa value, the tag value is 00. So it is going to compare with the existing tags, right, from first to last. So it is matching. That means the cache hit is there. So the data which is there inside the cache, that will be retrieved and given to your CPU. So unless in direct mapper cache, this third access is a cache hit to slot 0. Then in the next, the fourth data which is accessed at the location 108. So that's tag value in the hexadecimal is 04. It is start comparing from your tag 00. Then it is comparing with your tag 04. So 04 is matching. Then there is a hit. Okay. Again a cache hit, unlike the direct map. Then comes to in the fifth data access time, it is 05C. The binary value of 05C is this. So the last 6 bits are your S bits. First 6 bits are your tag bits. From this tag bit, it is calculated as the tag value in hexadecimal as your 01. So this 01 is going to compare with this, not matching. Then compared with the next tag, not matching. Then it is going to check that the already existing tags are not matching. Then there is a no slot has the tag 01. So a cache miss occurs. So pick the third one, which is the from these empty 2 slots. Pick the first one. Pick the first empty slot, that is slot 2, to store the cache line. Of 64 bytes from your address was 04. Okay. So then the goes to the next time, it comes as your 101A0 address. Then to find out its tag value. This tag value again compared with all of this, not matching. It is not matching. 06 not matching. Then understand that no tag are matched. That means no slot has your 06 hexa value as a cache miss occurs. So then it picks the the empty slot, and that will accommodate the cache line. that will accommodate this cache line. Okay, so with this, then the seventh data axis, in the seventh data axis, its hexa value is 02B. So this 02B again compared with every compared with the every hexa value in the tag. Okay, previously it is previously this value is 00, right? The previous 0 is 00. Okay, that is not matching. So then once this entire cache is filled, then it must take a replacement policy. In the replacement policy, it takes that first in, first out. So first this frame was filled, so that will be taken out. That will be taken out and filled with the and give the pick the oldest slot, and that slot stores this new cache line. Stores this new cache line with this address. New cache line with this address. So here we use very simple replacement policy as just choose the slot, the oldest one, or the first come first out. So first come first out. Okay. So what are the pros and cons of this one? Means this is much the pros are the much fewer cache misses in this case compared to a direct access, and than other cache placement policies. The cache miss only occurs when the cache is not large enough to hold all of the work sets. But in our previous example, there are two cache hits. There are two cache hits, whereas in direct mapped caches, there are no cache hits for there. So the problem in this fully associated one means if the cache size is increased, suppose if the cache size is increased and that size is having the tags, suppose 1 to n. So for every new tag, it is going to compare. It is going to compare. Okay, n times. N comparison will be taken place. If it is not matching, they're going to compare next one. They're going to compare next one. They're going to compare next one. So the number of comparisons will be increased. So that will take a long time to compare the tags for all slots. That is the only disadvantage of this one. So to overcome from this problem, there is another method called the set associative caches. This set associative caches is the combination of your directed mapped cache, which has too many misses, and fully associative cache, which has too slow because of the lot of comparisons. So we can strike a balance between this miss rate and the cache speed. So what happens here, the set associative caches combines the idea from both the directed map, that means zero address the cache line, the cache line index will be assigned to a zero indexed set. We call set index. Instead of frame, we use the set index here. So then the direct mapped cache and fully associative cache will be balanced in this case. So what happens here, the concept in set associative is whatever the cache is having the frames, instead of assigning in direct mapped caches, the zero cache will go and take in zero frame, one cache will go and take in one frame, like that. So instead of that, what happens, it is divided into caches as your sets. Okay, like set 0, and the next one is your set 1. Okay, it will take set 1, and after that, once this selecting set 0, set 1, it is just like your direct map caches. And once the set is selected, inside set the frames will be there. Those frames can be filled in any manner. Those frames means any empty frame can be given to the upcoming cache lines. So in that ways, the complete cache can be utilized, and it will reduce the number of miss rates, as well as it can speed up the cache load or cache storage, the cache line storage in the cache. So as said, a cache is partitioned into sets of your slots, and for every set, the set ID for a memory address will be given and can be directly determined, similar as your direct map to cache. So within a set, there are several fully associated slots. As said, there are fully associated slots, okay, in every set. So these slots are these frames, we call these frames. A cache line mapped to this set can be stored in any of these slots. So here the concept comes that n-way associative cache. N-way associative cache means how many frames allotted, or how many frames are there in one set, in set one. In every set, how many frames are there? Every set size is fixed here. Every set size is fixed here. So this n-way associative is a set of, in this case, suppose we have 1, 2, and 3 are there, then we call this as your three-way set. Three-way set. If it is taking suppose 4, then we call it as your four-way set. Four-way set. Then how to find the number of the size of your cache? The size of your cache can be calculated as number of sets. Number of sets. So we call the like number of sets. Number of sets multiplied by how many frames are there in set. That is the number of frames. So the number of frames, we can call that as your ways, number of ways. Okay, so that is your n-way, we can say. That is multiplied by what is the size of this one. The size of this one is 2 to the power of s. That is size of your cache line. That is 2 to the power of s. So you can write your size of your cache is equal to your number of sets. The number of sets, let me call number of sets are y, multiplied by number of ways, multiplied by 2 to the power of s. So from there you can also find that how many sets will be there, how many sets can be there in the cache line, that you can calculate that your x, the size of your cache divided by number of ways multiplied with 2 to the power of its cache line size, that gives the number of sets in that cache line. Okay, so from here we are using the direct mapped concept for sets, not for frame. So we use the set index. We use the set index in this address. So this is similar to a direct mapped cache. So few bits in the memory address is used to determine the corresponding set index. So how many bits are means, if there are two sets are there in the frame, if there are two sets are there in this cache, set 1 and set 2, to represent these sets, it requires 2 to the power of the 1. It can use is equal to 2, right? Is equal to 2. So it takes only 1 bit is enough to represent these sets. So after s bits, the lowest 1 bit will be taken for set indexing. Remaining bit will be taken as your tag. So if there are two sets, then there is only 1 bit for set index. And for this address, suppose 129, the binary form of that one is this. So last 6 bits are used for your s bits, and this bit is used for your set index, and remaining are used for your tag purpose. So from here, how it is going to organizing the set associative organization means, first, what happens? It is going to select this set. So from this address, the set index bit will be given as an input to your decoder. From that decoder, it is going to select which set it will be. Okay. After the set is selected, from that set, it follows the fully associative mechanism. In fully associative mechanism, there are 4 in every set. In this case, is a way 0 to way n-1 is there. So in every way, suppose let us take set 1 here, set 1. In this set 1, it is having the number of frames, that is way 0 to way 1. We call way 0, your way 1, your way 2, and so up to way n. In this way n, every way you are having the tag. In every way, tag will be there. After that, status and data will be there. So all these, if this set 1 is selected, then from this, whatever these tags are there, these tags will be taken for comparison operation. So this all these sets will be taken, okay, from this set one, okay. All these ways from there, all tags will be taken, and all those tags are compared with the tag of your address which is given. If it is a hit, if it is matching, if any one tag is matching, any one tag is matching, so the from all those tags, the data will be given as an input to multiplexer. From there, the whatever tag is matched, suppose for example tag 1 is matched, so tag 1 data 1 will be given as an input to your select word. From that data, whatever the part is required, that is given by your offset. So that offset will select this part from this data of this, and that will be given as an, that is a word, will be given as an input to your CPU for processing. So with this, what happens, the number of, we'll see the example. In this case, again, consider the same, the reference of your memories. Okay, the cache representation looks like this. There will be set 1, set 0 is there, and set 1 is there, and in that set 0 there are two ways are there. So it is two-way set associate cache with the two sets. So there are 4 slots in total. Cache line is your 64, so S bits are 6 bits, and the reference memories are given this. So these ways are represented as 0 way, 1 way, 0 way, 1 way. So initially the cache is empty. Initially the cache is empty. When initially the cache is empty, the valid bits are set to be 0. That means no data is there in that. So when they are set to be 0, initially cache is empty, so all valid bits are 0. So then first data access, which is located at the first reference address 000, the binary form of that one is this. So last 6 bits are your offset bits, all 6 zeros. Then cache line starts with your cache line starts with these bits. Okay. So that the tag value in the hexadecimal you can write 000. So once this is there, then what happens? The in our case, two ways are there, means one bit is selected. So last 6 bits, these 6 bits are your offset, and this bit is your set bit, set selection, set index. Set index means your 0 set is selected. In that 0 set, once the set is selected, then it follows the fully associative cache. In fully associative cache, what happens? Whatever the tag address is there, the tag address, that tag address is going to search whether it is there or not. So initially it is not there. So no tag address there means there is a data mesh, cache mesh. So it pick the first empty slot in the way 0, first empty slot in the way 0, first empty slot in way 0, and it load or store this data in the data field and set that valid bit as 1, and the tag address is 000. Okay, so then comes to the second data accessed at the location for 108. The last 6 bits are your S bits. Okay, and index bit is 0. That means set 0 is selected. In that set 0, the its a tag address, the remaining this value from here you will get the tag address is from here it gives 2, right? So hexa value of your 2. So this 2 will go and compare with the existing one. If it is not matching, then there is a the slot in the set 0 as tag 00. The cache is missing. So pick the first empty slot in the way 1 in 0, and that will load it. Okay, and then in the third one at 00, when it finds the tag and the set index is 0, so in set index 0 index, it is going to compare with this tag address. It is matching, so there is a hit here. There is a hit. So in the fourth data access case, again the set index is 0 from its binary form, and the tag value is 001. So first it goes to set index 0. From there it start comparing with this 02 with this, not matching. Then compare with this one, it is matching. So there is another hit here. Right? Then in the fifth data access, your set index is 1 and your tag is value is 001. So in set index 1, it goes to set 1. It leave this set 0. So in set 1, it is going to check whether this index is, whether this tag is there or not. So initially it is not there. Here this is empty. So it gives that the set 1 has tagged this 0 1. Okay, so that is miss occurs. So pick the first empty slot way 0, that is first in first out, right? Way 0 is selected in set 1 to store the cache line 1. So note that way 0 of set 0 also has tagged this, and the as long as they are in different sets, they will never be accessed at the same time. They will never be accessed at the same time. So the sixth data access at this 1A0, then set index is 0 here, and the tag address is 03. So it goes into your set 0. In set 0, this is going to compare with the previous one. In the previous one, it was your 00, actually 0x00, not matching. Then compare with this one, not matching. Then there is a miss occurs. So the first come first serve basis, the first frame become evicted. This will become evicted and give space to the new tag address of this one. So unlike your fully associative cache, this sixth access caused a cache eviction when there is still empty space in the cache, because this space is still empty. But whereas in fully associative, this is not. This will take place. So in the seventh data access, index is 1, and your set index is 1, and the tag address is 15. It goes to set index 1 and compare this tag address with the existing one, not matching. So it will going to take place. So cache miss occurs, and it pick the empty slot, that is way 1 in set 1, and store the cache line in that. Okay, so what are the pros and cons of this one? Means it is fewer cache misses than the direct mapped caches. In the previous example, there are 2 cache hits we have identified, which is similar to your fully associative cache, and which is simpler for implementation and faster than fully associative cache. So this set associative cache is a trade-off between the cache miss rate and the implementation complexity of your latency. So more ways means lower cache miss rates, less ways means more cache miss rates. So but a higher complexity and the higher latency is there. So a directed mapped cache is essentially a direct cache mapped is essentially a one-way set associative cache. So a fully associative cache is essentially a one set associative cache that will all lines in this form. So what's the problem means no much of the cons, but it is different to determine the best number of ways. So to how to determine this best number of ways and determine the best number of ways, this is like all engineering parameters. The benchmarks can help us to determine the average best number of ways for the special use cases. So this cache miss rates for different number of ways of your the spec tools benchmarks, which we have discussed in the previous lectures. Okay, that gives that for one way the data from the from one way the miss rates are less, but as this number of ways are increased, then the miss rates are gradually decreased. So from there, if you see the raw data, that if cache size is 4 kilobytes, suppose in one way miss rate is 0.098, two way 0.076, four way it is this. So from this table, it is concluded that by following this mechanism, the latency, the average memory access time latency, by following that to determine the best number of ways, it gives that the average memory access time is always gives the cache sizes that based on is the best way for this determining the best number of ways is always your two ways far better, four ways also okay, because if you see the number changes, there is not much difference here. There is not much difference. So at one at last, the note how the average memory access time deteriorates with more moves, means sometimes it gets worse than one way, and in cells with the red numbers. So one last thing, the numbers are fairly old. The modern processors are usually uses the 16 ways caches as the hit latency. That does not demonstrate that the fast cache. Does not demonstrate the fast cache. So with this, I would like to stop the session, and